The motivation for this project is to demonstrate the principle of Newton's second law of motion, which gives the relationship between the net force, acceleration, and mass. The equation used to quantitatively visualize the application of Newton's second law is the following. A equals F net over m, where A is the acceleration, F net is the net force, and m is the mass of the object. Our goal is to determine if an object with greater mass will experience a smaller acceleration and net force than an object with a lighter mass, because acceleration and net force are inversely proportional to mass. We also seek to confirm the presence of unbalanced forces that causes objects to accelerate with an acceleration that is directly proportional to the net force and inversely proportional to the mass. The physics concept used in this experiment was the principle of Newton's second law of motion, which gives the relationship between the net force, acceleration, and mass of an object. The slope of the velocity versus time graph will be used to find the acceleration, which is the rate of change of velocity divided by the change in time. Even more, the graph will reveal an initial segment with a constant positive acceleration, a middle segment with zero acceleration, and a final segment of constant negative acceleration. Furthermore, the force of each object will be compared using the following calculation: f of x equals g sine theta, after acceleration has been calculated. The final velocity, which is equal to the acceleration, was found with v equals the square root of 2gh. The resulting predicted and observed forces were compared and analyzed. For our predictions, we believe that the heavier car would have a lower acceleration and incline force higher than the lighter car. And we also hypothesized that the free fall is not in effect due to the inclined plane. In terms of our observations, we saw that the heavier car had the same acceleration as the lighter car, and that the heavier car had a greater inclined force than the lighter car. In both cases, mass is negligible, free fall is not in effect, and the angle impacts the final velocity, and therefore the acceleration. The distance on the ground from the table to the end of the ramp was 72 centimeters. The height of the track from the ground to the table was 74 centimeters, and the length of the track was 103 centimeters. Also, the angle of the car was 45.9 degrees. The predicted acceleration for both cars was 7.04 meters per second squared. The predicted force of car number 1 was 0.32 newtons, and the predicted force of car number 2 was 0.24 newtons. Moreover, the final velocity of the energy was 32.3 meters per second for both cars, and this was equal to the observed acceleration, 32.3 meters per second squared. The observed force of car number 1 was 1.5 newtons, and the observed force for car 2 was 1.1 newtons.
Trial 1, 3, 2, 1, go. Trial 2, 3, 2, 1, go. Trial 3, 3, 2, 1, go.
For our results, the heavier and lighter car had the same predicted and observed accelerations of 7.04 meters per second squared and 32.3 meters per second squared, respectively. The heavier car had a greater predicted and observed force from the incline than the lighter car, and the mass had no effect on the acceleration but did have an effect on the incline force. The final velocity was needed to account for the angled car track and find the expected acceleration and force. Here is our graph comparing velocity against time. In conclusion, this experiment revealed that objects with different masses will have the same acceleration but will experience a different amount of force. This is because the force from the incline does not take into account the masses of the object, as it only depends on the angle and acceleration. Even more, it was essential to not only consider the final velocity of the system due to the angle of the car track, but also the relationship between final velocity and acceleration. More precisely, the final velocity and acceleration will be equal because there is no change in direction and the toy cars are starting from rest. Based on the predicted and observed measures of acceleration force, it is evident that acceleration will be equal for both objects, since mass is not accounted for, but the forces will vary because of the difference in masses. Therefore, our original hypothesis is partially correct in that a greater force was needed for the heavier car and a lesser force was needed for the lighter car. However, contrary to our hypothesis, the heavier object did not experience a lesser acceleration than the lighter car because the force from the incline was not affected by the mass of the object.